Welcome to section 4.4, where we'll use applications of exponential and logarithmic functions. And a couple of things we want to do is we want to look at the graphs of some more complex functions other than just straight exponentials and logs. And we'll use calculus to sort of help us find the extrema of these functions and use them in real-world situations. Our first problem deals with the function f of x is equal to x times e to the 3x. So, and this is kind of a long problem, so you might want to write small. So the first thing I want to find are the zeros. The zeros are when f of x is equal to 0. So I'm going to set x e to the negative 3x power equal to 0. We're going to split that up. X is equal to 0, and e to the negative 3x is equal to 0. Well, we already know that this last equation here has no solution, and so the only 0 that we have is x equals 0 itself. So that tells me it goes through the origin. So that's one part of the graph. Now what about the end behavior? The end behavior is what the graph does on the ends, on the left and the right end. So I'm going to look at the left end here, and we do that by finding the limit as x goes to the left side, which is negative infinity, of x times e to the 3x. Well, this one is just sort of does itself. If I look at each individual piece, as x goes to negative infinity, the function x goes to negative infinity because it's the same function, it's x. And then now what about e to the negative 3x? Well, for that one, I'm going to show you a little graph. This is an exponential graph that looks like this. And you may be asking, well, why is it the decreasing graph and not the increasing graph? It's because the base is technically e to the negative 3, which is 1 over e cubed, which is approximately 0.05. Either way, we know that it's less than 1 and still positive, so it is the decreasing graph. Well, with that in mind, then this piece goes to positive infinity. And although you're not technically allowed to multiply numbers like this, we can sort of use it conceptually and say negative infinity times positive infinity would be negative infinity. Really large negative numbers times really large positive numbers are going to result in really large negative numbers. So this is negative infinity. So the left side goes to negative infinity. Now what about the right side? So the right side would be the limit as x goes to positive infinity of x times e to the negative 3x. To do this one, I'm going to make a little change here. I'm going to rewrite this as x goes to infinity, the limit as x goes to infinity, of x over e to the 3x. Because the exponent was negative, I can shift it down to the bottom. Now what do we have here? As x goes to infinity, the numerator goes to infinity, and now the function is y equals e to the 3x on the denominator. Y equals e to the 3x as x goes to infinity also goes to infinity. So this one is going to infinity as well. So this one is infinity over infinity. Now what do we do to evaluate a limit when it is infinity over infinity? If you're screaming at your computer right now saying L'Hopital's rule, you are correct. We take L'Hopital's rule, our favorite. And so this tells me that this limit is also equal to the derivative of the top, 1, divided by the derivative of the bottom, which is 3e to the 3x power. I did that by using the chain rule. The derivative of e to the 3x is e to the 3x times 3, but when they're linear like this, you see the pattern, you can just bring the 3 out to the front like that. Now what do we have? Well, the top is equal to a 1, so we know that L'Hopital's rule can't be used anymore. What is the bottom doing? Well, the bottom is still this same exponential graph multiplied by 3, so it's even more positive than it was before, if that's possible. And so this is going to infinity. So the bottom is going to infinity, the top is staying the same, and we know that that means that the whole fraction is going to 0, because as the denominator gets larger and larger, the fraction itself gets smaller and smaller, approaching 0. So those are our two end behaviors. On the left side, it's going to go down toward negative infinity. On the right side, it's going to level off to 0. This is a horizontal asymptote in that case. And the left side does not have a horizontal asymptote. It goes to negative infinity. All right, next we need some derivatives. So I'm going to go ahead and take a derivative here. So the derivative of x times e to the negative 3x is 1 times e to the negative 3x, unchanged, plus the derivative of e to the negative 3x, which is e to the negative 3x, times the derivative of the exponent, negative 3, times the x unchanged. I'm going to factor out e to the negative 3x, and that's going to be 1 minus 3x. And that's equal to 0. So we split it up, and we get e to the negative 3x equals 0, and 1 minus 3x equals 0. So this first one, no solution, because it's an e to a power. And the second one, we get x is equal to 1/3. Let's make a sign chart. So we get 1/3, and then we get 0. And we're going to test in this version of the derivative right here. And the only thing we really need to test in is the polynomial part, because we know that e to the negative 3x power, that this is always positive. Because it's an e to a power. So the only thing we want to test is 1 minus 3 to 3x. I'm going to test at 0. And if I plug in 0, I get a positive. So this is going to be positive. And the multiplicity of the 1/3 was odd, so this side is negative. That tells us that the function is increasing followed by decreasing. And that we have a maximum right here. All right, let me rewrite the derivative. This was e to the negative 3x times 1 minus 3x. And now we need to take the second derivative. So it's going to be the derivative of the first, e to the negative 3x times negative 3 by the chain rule, times 1 minus 3x, unchanged, plus the derivative of the second term, which is just negative 3, times e to the negative 3x power, unchanged. Now let's simplify. I see that I can factor out negative 3 from both terms. I see that I can also factor out e to the negative x, negative 3x rather. And that leaves me with 1 minus 3x from right here. And leaves me with a plus 1. So I still have to have a placeholder for this second piece right here. And since I factored everything from it, then I have to represent that by a 1 so that if I were to redistribute, that piece would come back into play. Let's simplify. So this is negative 3 e to the negative 3x times 2 minus 3x. Let's set that equal to 0 and solve for x. So the first term is negative 3 equals 0. That's no good. Then we have e to the negative 3x is equal to 0. And we have 2 minus 3x is equal to 0. So nothing from the first, nothing from the second, but we do get x is equal to 2/3. All right. Let's make a sign chart for the second derivative. I'm running out of space, so let's go ahead and put it up here. So second derivative in x and let's test at x equals 0. So we have, let me write out the signs here. The negative 3 is going to always be negative. The e to the negative 3x is always going to be positive. And then this one is the one that can be changed. So if I use x equals 0, I get 2 minus 3 times 0, which is positive. So at 0, we have a negative. And the multiplicity was odd, so it changes sign there. Now what does that tell us? Well, this is a second derivative. Second derivative tells us about concavity. So in the first interval, it's concave down. In the second interval, it is concave up. Now we can, and that gives us an inflection point. Now we can use all of this information to draw a little sketch of the graph. The first thing we know is that it goes through 0, 0. We also know that it has a horizontal tangent line, a horizontal asymptote on the right side. So we'll draw that in. And now here we go. So it starts down at negative infinity. Between negative infinity and 1/3, it is increasing and concave down. And then it reaches a maximum at 1/3. Then at 2/3, it's going to have an inflection point. So we've reached the maximum for where it was increasing. Now it's going to be decreasing, and then we have an inflection point, and it continues to decrease forever, and it settles in on its horizontal asymptote, but it's now concave up. So it's like that. And that's sort of what the graph looks like. If you want a better representation, you can always graph it to see these in action, but the numbers are very small, so you're going to have to zoom in really close and tight to the origin. Example number 2. Bob owns a piece of land whose value t years from now will be v of t is equal to 12,000 e raised to the square root of t power dollars. If the prevailing interest rate remains constant at 5% per year compounded continuously, when should Bob sell the land to maximize its present value? All right, so this is an optimization question, and we're trying to optimize present value. So let me derive a couple equations here for you. We had this equation for continuous compound interest. And if you solve this for present value, which is P. We called it principal, but that's sort of a a more general way of thinking about it. This is the present value, and A is the future value. All right. So if we solve for P, then we get A divided by E to the RT is equal to P. And I can rewrite that by moving the E to the RT power back into the numerator and negating the exponent. So this is a formula for present value if something is going to be compounded continuously. Now, what we know is that we can create this function P of t equal to A times e to the negative r of t, but the A is really going to be this future value. And the future value of the land comes from the v of t function. So I'm going to change this to v of t, e to the negative rt. And I'm going to bring in our numbers now. So the v of t function was 12,000 e to the square root of t times e, and the prevailing interest rate was 5%. So I'm going to substitute that in for r. The negative is now part of the formula. So it is negative, the exponent is negative 0.05 t. And then we can simplify this. And because they're both base e, we can add the exponents. And we get square root of t minus 0.05 t as a power. This is a function of time that gives us the present value, and we want to maximize that. So how do we maximize something? Well, we take a derivative. So 1200 times e, the derivative of this is just the same function, times the derivative of the exponent. So the derivative of the square root of t is 1 over 2 square roots of t, minus the derivative of 0.05 t is just 0.05. Now, it might make this easier to work with if you know what 0.05 is. It's actually 1/20th. So you can change it on this one. You might not be able to change it on some of the others, but this one will work out well. All right. Now, to find where the maximum occurs, we need to find the critical values. So we're going to set it equal to 0. So setting this equal to 0, we would get 12,000 equals 0, which is no solution. We would get e raised to the square root of t minus 1/20th t equals 0, which again, no solution. And the only real thing that happens here is 1 over 2 square roots of t minus 1 over 20 is equal to 0. I'm going to multiply both sides by 20 root t to clear out denominators. And that is going to give me 10 minus the square root of t is equal to 0. Move the square root of t to the other side. We get 10 is equal to the square root of t. And to solve for t, square both sides. T is equal to 100. So there's our critical value. Let's look at the sign chart to ensure that this is in fact a maximum. So this starts at 0, and because it's the present value, and it goes on for years. It's 100 years there, so we'll put that in there. And if you test the p prime at some number between 0 and 100, you get that this is positive and then negative. So that tells us that it is, in fact, a maximum. We have a continuous function, so this is an absolute maximum. And so it's 100 years that it would take for him to maximize the present value of his land. So it's something for his kids and grandkids to think about, perhaps, but maybe not Bob himself. All right, that's it. Thanks for watching. We'll see you next time.